Welcome to Model 1.3, where we will be talking about how you can change the shape of the cells in CompuCell. Okay? So, like before, we'll be doing simulation with just a single cell, so we can show the many ways that you can actually control the shape of the cell and what affects the cell to be in a given shape or not, or a different shape. So again, the meeting will be recorded and live streamed on YouTube. Um, I have my chat open here. Please send questions anytime you have a question or a doubt, or when I ask you guys question, please also answer in the chat. Okay, so well, the motivation will be cell shapes, and then I'll give a step-by-step exercise by working different modules. Well, I guess many of you know that cells come in a variety of shapes. You can see cells of many different shapes. So last time we talked about the difference between epithelial cells and mesenchymal cells. Okay, one is more, the epithelial cells tend to be more square or columnar, although you also have more flat squamous epithelial cells. The mesenchymal cells are usually have very regular shape and spread in a two-dimensional surface, or can be more like a fibroblast and be spread within the ECM of in the connective tissue. You also have cells like your blood cells, skeletal muscle cells, nerve cells, that are a very drastic example of a cell with a very different shape. So, given the variety of cell shapes, you may ask, okay, how can we model those things, or to some extent, in the CompuCell using the CompuCell player, CompuCell simulations. Okay. So, okay, I already talked about the variety of epithelial cell shapes, and the mesenchymal cells. They're regular, but they can be irregular there are different types of regularity. They can be irregular in a particular way with some regularity on it. For example, mesenchymal cells can be completely like an aster-like, or they can be bipolar or monopolar, right? And here is an example of human fibroblasts and neurocrest cells, many different shapes. And we already saw in the previous module that by tuning the contact energy of our cells, we can actually get cells that are either round or look a little bit more irregular. So the plan for today is for now, is going to be to explore other energy terms in our energy function that can regulate and that affect the shape of the cells. Okay. Cool. So let's do some step-by-step exercises, and I'll also be teaching today how to change parameters in the player while simulation is happening, and also change parameters, also how to plot parameters live during your simulation. Okay. So let's start to open up your CompuCell3D on either NanoHub or on your desktop, and let's create a new simulation. Okay, so open 3D, go to CompuCell3D project, new CompuCell3D project, click there, and let's give a name for the simulation. My suggested name is going to be module 1_3_ cell shape. Okay, and again, let's select Python plus XML. Okay, so we have already gone through this in the previous module. I assume that everybody's already know more or less how it works, so we can go a little bit faster. So in the next window of the wizard, I want to already make a change there. Okay, because we'll be simulating just one cell, I want to have a smaller simulation space. So I ask you to change the X and Y simulations from 256 pixels to 100 pixels on both of those entries. Okay, so in line estimations, change this and this to 100. Okay, and you can leave everything else as it is. Okay. Is everybody with me? Okay, so if you have done this, you can then hit continue and proceed to the next step. And again, we have to give a name for ourselves, okay? And the name that I'm using in this module will be test cell. The cell going to be test different values, but you can give whatever name you want. You can give that your own name. You can give that endoderm, mesoderm, fibroblast. Can be whatever you want, okay? So I'll give just test cell, but again, make sure that you write the name of your cell type here and then hit add button and make sure that it's populated here in the table before you hit continue. Okay. Yes, we can go back. Here in the previous slide, we just have the general simulation properties. The only thing I'm asking you to do is to change the X and the Y from 256 to 100. Everything else you can leave the same. You're welcome. Okay, so again, in the next slide, write the name of your cell, hit add, make sure it appears on the table, okay? And once you have medium and test cell in the table, you can then hit continue to proceed to the next window. If you miss something on the window, you don't think you did it right, you can always hit the go back button and go back to the previous options. Okay. So again, we will not be using any chemical fields. That will be for tomorrow. You can just hit continue. And now here, you want to select many things. Okay. So I want you to select contact because you'll be playing with the contact energies. I want you to select volume because the cells must have a volume, okay? Then I want to select surface flex as well. We'll be using the surface constraint on the cells. And I also want to finally hit length constraint. So the cells also may also change the length of the cells, okay? So make sure you have those four options here selected: contact, volume flex, surface flex, and length constraint. We will not use all of them at the same time. We will then turn them off, but then as you go through the module, you will be turning them back on and see what their effects on the simulation will be. Okay, if everyone select this, then I can hit continue and the configuration is complete, right? And with this, let's just select, you should pop up here the name of your model. Just right click and click open in player or select it and click on the CompuCell3D logo, and that should launch your simulation in the player, okay? If you are just using your same, if you did not close or tweet it from the previous session, from the previous module, you may see two simulations here, the previous one and this new one, okay? It's okay, you can just collapse the old one and tell the tweeter to play the new one, okay? So did everybody have their simulation up and running? If so, tell me, what do you see? Around the blob with multiple cells. Yes. Elongated cells in a ball that look very nervous. I like this description. Okay. So you see that the niche condition is very similar to the one before. We have started with multiple cells. And if you just stop and play simulation again, you see that the cells start as squared as before, but now the shapes are very different. Okay. Why they are like that? Okay. They should see something like this. Why the cells look this shape now? So the most drastic change here is that the cells do not look round, they look elongated, right? Why they are elongated? The PowerPoints should already be available on the CompuCell on our Google Drive. Yes, Fatima got it. Is because we did select the length constraint in our properties, okay? And when you select those extra energy terms, they already start with predefined values there, so they're already working on when you run simulation. So the cells do have a length constraint and is already working, and that's why you see the cells are elongated. The cells also have a surface constraint, okay, and addition values and volume constraints. So all this together gives up this end result that you see on the screen, okay. But we don't want to work on all of them at the same time. The first thing we want to do is first reduce our simulation to just a single cell and turn off the other constraints. So let's do the first thing, which is instead of start with how many cells here? 81 cells. Let's start with just one cell, and I want cell to actually be bigger so you can appreciate the effects of all the energy terms on it better. Okay, so first thing I would like to do is to go back to 3D, stop your simulation, go back to 3D, expand the simulation to see all the 3 cell simulation files, and then I want you to again open up the XML, right? And then I want you to go into the uniform initializer plugin that you have at the very end of the configuration file. Okay, so if you go to which at about line 57 at the very end of the XML, you have a steppable called uniform initializer. Okay, this is called steppable because it's done at zero step of your simulation before the simulation starts, and this is where you actually draw the initial condition of the cells. We have the uniform initializer. We also have the blob initializer. The uniform initializer makes a square or a rectangular initial condition of cells, while the blob initializer will make a round up cells, okay, round up tissue. But here in this case, you're using the uniform initializer, and the way it works is the following. It basically draws a square or rectangle in your 2D simulation, where you have to specify first the minimum the coordinates of one corner and the coordinates of the opposite corner, and what the CompuCell will do, we will just fill up this space with cells of a given size. So here in this case, what you have at the beginning is the minimum box is 20, 20, and 0. Okay, so it starts at here. Okay, I didn't draw this very well, but okay, you got it. It should be 20 by 20. And the box maximum will be the coordinates of the opposite end, which will be 80, 80, and z equals 1. This z here from 0 to 1 just means that you are doing a two-dimensional simulation. So there is the depth of the z is just 1 pixel. Okay, so you got those two coordinates, and then you're going to fill up with cells, and the size of your cells will be 7 by 7. That's what it means by this width here. So you're going to be 7 cells here, 7 cells here, 7 pixels, 7 pixels. So the first cell went from 20 to 27 and 20 to 27 on the y, and then the next cell going to be from 27 to 34, and then 0 20 to 27. Okay, and then this fills up then you proceed to the next row, next row, next row, next row, and then you fill up this whole thing with cells. So that's how the uniform initializer works. Oh, sorry. And you have also to tell which type of cells you can have here. In this case, you only have one type of cell, test cell. But we have simulation where you have the test cell, and test cell 2, and test cell 3. You can just write all the cell types here, and they're going to be a mixture of all those cells in between there. Okay. You can also specify the gap. Instead of have all the cells starting right next to one another, you can add a 1 pixel gap between them, so they start with a little bit of gap between them if you want. So that's what this gap means. Okay. So if you have many constraints, target length, surface length, volume, what you do, you sum up all those energies and you minimize the global energy of your system. Okay. You don't minimize one at a time, you do all of them together. You may be in the situation where you're minimizing one constraint while increasing the other constraint. Okay, that may happen. Okay, so they may be at odds with one another, and actually you want that. That's when your simulations becomes more interesting, when you have different things compete with one another, and then you favor one versus favoring the other by changing the parameters, and then you can see the effects that has on the cell shape and behaviors in your model. Okay. Okay, so the first thing you want to do, you want to reduce this initial space. Instead of from 20 to 80, I want you to be 40 to 60. So that's what I'm asking to do now. So you change the box mean from 20 to 40, and the box maximum, both x and y values from 80 to 60. So now we have a smaller initial space. Okay. And the other thing I want to do is to make your cell to be 20 by 20. So you change the width of the cell from 7 to 20. So in this case, you start with one big cell on the simulation, because that's the only one cell will fit within your box. I will explain what length constraint does. Well, basically it tells all the cells to have a given length on its major axis. Okay. So that's why the cells are elongated, because you didn't want your cells to be about 7 by 7. You want one of the axes of the cell to be, I don't know, 20 pixels. So that forces the cells to be elongated. It doesn't specify if you elongate in this direction or this direction or this direction. That will happen by chance, but it does make the cell to be more elongated. Okay. So please change the initial size of the box to be 20 by 20. So it goes from 40 to 6 on the x and 40 to 6 on the y. And change also the width of the cells from 7 to 20. That will be your next slide. Okay. So now you only fit one cell in that initial box. Okay. So that will be on line 64. So once you do this, you can then save your simulation, because we did make changes to the XML. So again, well, you can either hit this button here or click File, Save, or Control Save or Command Save, Control S or Command S if you're on the Mac. You saved simulation. This icon here turns from red to blue, means that it's saved. And after that, you can actually run the simulation, and you should see something that looks like this. So I'll give you guys a little bit of time to try that, and tell me if you get something that's similar to what I have on my screen. Thank you for, yes. Okay, many people are answering yes. That's great. So it's working, right? So, okay, that's okay. How we can navigate the earliest steps in the player? unless there was some great improvement that I'm not aware, you unfortunately you cannot do this. Okay, you can only see your current snapshot. You cannot go back to see the previous one. Yes, it would be great if you have that option to of going back the previous steps, but that's not a feature yet in the CompuCell player. Okay, so if you want to, yeah, this kind of happen very fast. So probably what you want to do, you want to stop simulation, and instead of hitting play to restart, you hit the step function, okay, and then you see one frame by frame what's going on. Okay, so if stop simulation and hit the button with the round up white figure, you're able to see this sequence of events in more slowly. Did it work? If you do that? Yes, okay, great. So what you see a cell that starts as 20 by 20 pixels and quickly reduces, okay, and still has a very funny shape. And then if you just keep playing, you're gonna be kind of wandering around in the space, okay. And again, it does not look a round cell. It looks a little bit elongated. And again, it's because all of those plugins are turned on at the same time. You have a competition between volume, surface, and lens constraint, and also energy. They're all working together at the same time. What you want to do now is to turn off at least two of them. Let's turn off the length constraint and turn off the surface constraint of the cells. Okay, and let's explore one at a time. Okay, so as I said, in the current simulation, you have 4 plugins, all working at the same time. Okay, and except for the contact energy plugin, which that it's kind of very different from the other ones, all those last 3 ones, volume, surface, and length constraint, work in a similar manner. You have to give them a target property, a target value. So your cells want to have this ideal volume and this ideal surface and this ideal length of the major axis, okay? And you penalize any deviation from that target volume, and you regulate the strength of each one of those constraints by changing the what we call the lambda parameter of this uh, of this of this energy term in your simulation. Okay, so they all have the same look, right? The same form is the current value minus the difference between the current value and the ideal value is squared. Okay, and that writes up a potential. Okay, quadratic potential, and then so any deviation from that will be penalized. So usually your cell will be around this target value, but not much deviated from it. Okay, so here I'm showing the case for the volume constraint, but the surface constraint will be the same thing, and the length constraint will be exactly the same thing. Okay. Okay, and again, you may have this at odds with this, at odds with this. Okay, it's okay. Then the strength of the constraint you set up which one will be the dominant one. Okay. So now let's do a very basic exploration. Let's explore the effects of volume constraint. Okay. So if you want to change, actually I don't need to go this. So what if you want to explore only the volume constraint, you have to turn off the length constraint and the surface constraint. So let's go to the go back to the XML code, untweet it, okay? And I want you to go into the place of the code where you actually specify the surface constraint. That's the surface plugin, which should be at around 931, okay? I think it will be in the exact same line for all of you, but if not, it should be more or less in the same place. And what I want to do is to turn off that plugin, and you can do that by just setting the lambda surface to be 0. So if you make this parameter 0, then your whole energy term will be 0. Okay, so it doesn't matter what the difference between your surface and the target surface of the cell is. You have no effect on the simulation because it has 0 weight on the total energy of your system. This is the same as commenting the line. If you want to comment this line, you have to select those 31, 32, 33, go to the menu and say block comment. It probably is a little bit better because then the plugin is just not called from simulation, okay? But commenting and uncommenting XML syntax can be a little bit tricky. It's better if you just set the lambda surface to 0. Okay, it's not the most efficient way computationally, but it's the most safest way to do it. Okay. So I strongly suggest you to just set the lambda to 0. Okay. Okay. So you turn that from 2 to 0. Okay. And then you do the same for the length constraint. That should be about line 54 in your XML code. Set the lambda length to be 0, and again you'll be effectively turning off that contribution to the shape of our cell. Okay, is everybody with me? So again, set on 32 lambda surface to 0. Does it matter if you set to 0.0 instead of 0? No, it doesn't matter. And here also set the lambda length to 0. Okay. Then let's save simulation and play in the player, and you guys can tell me what happens. So if you now play the simulation, it's, well, the effect is still the same as before, okay? The cell starts as 20 by 20, but and it shrinks, okay? But the shape is a little more isotropic than before, okay? It's a little bit more regular, okay? But the cell still shrinks. Why does the cell still shrinks if you set it to be 20 by 20 at the beginning? Target volume. Yes, Rose is right. What's the target volume of the cell? You can look at that on the XML. Please try to find out in the XML what's the target volume is. 50. James and Rosie already knew it. Okay.
Yeah, 50.
So if you do not want the cells to shrink, which value you have to set up for the target volume of the cells? 400. Okay, that's 20 by 20. Okay, so you can do that, but before you do that, I want you to actually visualize this decrease of the cell target volume over time using plots. Okay, so don't change the target volume yet. We can see visually that the cell is shrinking. Okay, but you can also see graphically the size of the cell shrinking. So if you plot the current volume of the cell over time, you should see a line that I do not know if my camera is inverted or not. Okay, but you should see a line that starts at 400 and then decreases, and then until it gets to 50. Do you agree? That should be doing like this if you plot the volume of the cell. Well, I hope you agree. Okay. So it will be very interesting to if instead of just seeing the cell in our simulation, we actually see a graph of the cell volume over time. Okay, so why don't we already do this in our simulation? And I can already show how to do this. So, and yes, the CompuCell3D can do plottings, and it can do many plots, not more than one, and it can do plots and histograms live during simulation, so you can see some properties of your cells, of different cell types, and you can see them and have all those plots being updated at the same time as your simulation goes on. Okay, so here is a drastic example of simulation that I did with Gilberto, where we have many plots. So this is a simulation of foam. It's not cells. This is a foam coarsening. Okay, and you have many plots of parameters over time. Okay, the resolution is not very good, but beside those plots, you can have plots with more than one line on them, with lines, dots. I can have a scatter plot. You can have histograms, and you can even visualize cells with different colors depending on the property. Okay, so these are all things that you learn as we go over the workshop. But for now on, let's just make a plot of the cell volume over time. Okay, so what you want to do, you want to plot this. So here is a plot. So this is the same simulation that you guys had, and this is a plot of the volume in red and the surface as dot points over time. Okay, and you want to see the volume decreasing, going up to 50, and also you can plot the surface area of the cells that increase momentarily and then goes back to a stable value. Okay. Okay, so let me show you how you can do this. Okay, assume that you all want to do plots in your simulations. Okay, but before you get to that, I have to give a step back and explain how your simulation files work in CompuCell. Okay, so you may have noticed that when you create a simulation in CompuCell, you not only have one file, you actually have three files. Okay, you have a Python file, an XML file, and then another Python file. Okay, did you notice that? Okay, so the reason we have three files is that those Python files is the ones that allow you to write user-specific functions in your simulation. Okay, so the XML file is the one that I have been using so far, which just consists of predefined calls to predefined functions to the CompuCell player. So, for example, here you have the metadata that we didn't use so far that specify how many processors you want to run your simulation. You have the plot section where you specify the dimensions of your system, the number of steps you want to run, the temperature, this the distance of the spin flips, the pixel copy flips that you make. You also have the list of all the cell types you want to have in your simulation. You make a call for the volume, the target volume of your simulation. Okay, you make a call for the surface plugin. You make a call to track the center of mass of the cells, and you make a call for the contact energies, and in the very end you have also a plugin that calls that sets the initial condition of the cells with the uniform initializer. Okay, so the XML file is used to specify your simulations. Your simulation cell, how many cells you want to have, what will be the properties of those cells, but we will all be using predefined functions in the player. Okay. However, as you progress in making more and more advanced and sophisticated models in CompuCell, at some point just calling those predefined functions will not suffice. At some point you want to write your own functions, okay, or make some kind of conditions. If the cells touch this other cell, it should die, or if the cells get this much nutrient, you should start moving, or the cells should divide at given these and these conditions. So you cannot all these kind of heuristic rules, okay, cannot be coded in CompuCell player. So what James did early in the development of CompuCell was add this Python functionality, so that allows users to write their own functions and own behaviors to the cells. Okay, and one thing that you can use this Python level of your code is also to make plots of your simulations. Okay, so I'll tell you how it works. So the XML, you just make calls for predefined plugins in your model, and then you have the Python files that actually allows you to write your own modules. Okay, so you see that you have two Python files. The first one is called the main Python file, and the second one is the steppable Python file. Okay, so the main Python file is used to call the steppables that we use in the model. So it's very short, okay, and it's basically saying import this function here and use this function at this given frequency of every Monte Carlo step. You're gonna call this user-defined function. Okay. These steppables are actually classes, coded as classes inside in Python, and you don't necessarily need to know what a class is. What you need to know is that it's a place where you can place user-defined functions in CompuCell. So this is the main Python file where it just calls these functions, and the steppable Python file is where you actually write those functions. Okay, so here, if you just look at that in your own code right now, the wizard already creates an empty steppable for you. So you all should have this model 1_3_ shape steppable automatically, but there for you. And it has a initial function module that just initialize the whole steppable, and then it has 4 predefined functions there: the start, step, finish, and on-stop. And they already comments on which one of what each one of those means. The start is the place where you write instructions that should be done at the very beginning of the simulation. The step is where you write functions or commands which should be run at every Monte Carlo step of simulation, or at every given frequency at which you call the steppable. The finish function is where is a set of instructions that you want to do at the very end of the simulation, and the on-stop function is the set of instructions that you want to do when you hit stop on the player and you kill the simulation. Okay, so right now this module here, this steppable, is already comes if by default in all CompuCell modules that you create from the wizard. And on the step, which is the one that we'll be using the most, you have the following command. You are going over all the cells in the simulation, and you are printing the cell ID. Okay, so each cell in our simulation has an ID, a number that differentiates one cell from the other cell, and this steppable here is just printing all the IDs of all the cells in the simulation every time it's called. Okay, so this is where you want to write your own functions and also this is where you'll be creating the plots in your simulations. Is this making sense so far? Do you guys have any questions? I'm not sure if I lost you or not. Okay, so that's the overview of why you have 3 simulation files in your simulation. So let's actually do something now, and maybe when you do something, things will become more clear. Okay, so let's now create a graph, and creating graph and plots have to be done on the Python level. So let's just click on the steppable file here that you have here. That should be the last one in the tweeted. Click there, okay? And what you want to do on the start function is to actually create the plot. And on the step function, we want to populate the plot with the current value of the volume and the surface of the cell, okay? So then you can ask, okay, how do I know how to create a plot there? I do not know what the Python command it is, okay? So the good thing about Tweetit is that is an editor which was created for CompuCell, okay? So actually you don't need to really know all the commands. You can actually get the commands from the menu. Okay, so what I'll ask you to do is to create a new line on 15 and make sure your cursor is right here on the same indentation level, okay? So make sure you create a new line and put your cursor right there. This is important, okay? That's how the way Python works. Python is very sensitive to the indentation level. So you leave your cursor right there, okay? Make a new line, leave the cursor right there on the line 15, right below at the same level as the S and the C, okay? At the S start and the C for the call. Put your cursor right there, okay? And with the cursor right there, you're gonna go to the menu and ask them to create a graph for you, okay? So how you do this? So in the menu, you have this CompuCell3D Python, okay? This is a list of all the Python commands that you can use, of both of the Python commands that you can use in your simulation, okay? So with the cursor there, go to the menu, CompuCell3D Python, click there, and you should see this list of all these options, okay? Then you can see they have addition, flex, cell attributes. There are many things you can do. You'll be seeing a good bunch of them, okay, in this course. So, but for here, for this module right now, I want to go and click on scientific plots, okay, which you should open this another set of options, okay, and I want you to click on the setup, okay. Setup, you're gonna set up your scientific plot, okay, and you see that a parenthesis there remind you that the setup comments should be on the start function of your simulation. Sorry, on the start function of your steppable, okay. So is everybody with me? So if you menu, CompuCell3D Python, scientific plots, click setup, okay, and it should paste the code for you at the exact place where you have your cursor on, okay. So tell me, so this is what you should be seeing in your on Tweetit after you click there. You should get those new lines from 16 to 22. Did everybody got this? Yes, Ruby, Elena, Kirin, Ivan. Okay, good. Thank you for using the chat. Okay. Over Zoom, we have no idea if the students are following you or not. If it was in person, I could see by your faces if you're lost or not. Over Zoom, there is a little bit harder. So I ask you to use the chat as much as possible. Okay, so here, what's going on? You have basically three commands, okay? One where you create the plot, and you can already specify some plot properties, the title of the plot, the title of the x-axis, the title of the y-axis, whatever going to be scaling, going to be linear or logarithm, and whether you want to have a grid in your plot or not. In this case, it has no grid. Okay, so that just creates an empty plot. And on line 21 and 22, you'll be adding different lines or different quantities to populate on this plot. Okay, so line 21 is having the a plot called M volume, okay, which will be a line of color red of thickness 5 points, okay? So we'll be using that to plot the volume of the cells. It automatically creates another line, which is the AIM-SUR, which stands for surface or mean surface, okay? And instead of being a line, it'll be made of dots of color green, and the size of the dots will be 1, okay? This will be very hard for you to see, okay? So I suggest that you actually change those things, and you can change the title of your plot, set from average volume surface, just volume and surface, because you'll be doing with only one cell. And instead of having the search to be green dots of size 1, let's make it cyan dots of a bigger size, okay? Because the background will be black, okay, and this green on black is not very good to the eyes, at least my eyes, at least for that size. So you can change that. You can also change the name of the quantity that you're plotting, because I'm not doing the mean volume and the mean surface. I just write volume and surface, but you can leave like that, okay? And I just changed the color to cyan because it's a little bit more visible. And I didn't do this in this screenshot, but you also can change the size from 1 to 5 to be much more visible, okay? You can also make the surface to just also be lines if you want, okay? So you can see that here that you can adjust your plot window to be whatever you want, okay? Is everybody with me? Do you remove M from, if you want to, you can do, that's what I did here, but this can be in principle whatever string that you want, okay? Just remove the M because M stands for mean in this case. Doesn't make sense, so I just changed it to volume and surface, but you can keep like that. It's just that when you add the value to the plot, okay, you have to be consistent with where you are adding the value, okay? So this, you just create a plot, and if you just save and run simulation, you create a plot that's black and empty, and your cell will be changing its shape, right? And there's nothing going on in the plot. That's because you have to actually fill the plot with values, okay? So that's what we'll be doing now, next on the step function, okay? So what you want to do next is to go to the step function, okay? We have to go over you have to grab the cell, so you have to keep that cell loop there, that's still line 34, and we don't necessarily want to print the cell ID, that does nothing for us, okay? So what I will ask to do is just delete the comment on line 36, but leave your cursor right there, okay? So delete this, but leave your cursor at the very beginning, okay? Because that's where you're gonna place the comments that fill up the plot. So inside step function, let's delete line 36 and leave the line or cursor right there at the same annotation level. And now I want to go again to CompuCell3D Python, scientific plots, and now I want you to select the second command, which is the add data points, okay? And you can see that in parentheses is telling you that this command should be on the step function, okay? So again, delete the line 36, leave your cursor there, then go to the menu, CompuCell3D Python, scientific plots, add data points, okay? Click there, and what you should see, should paste two commands for you, commands, which is add data point to this and this volume, okay? So you may have changed or not the name of the line or the quantity that you want to plot. If you change, you have to make sure it must match. If you did not change, you don't have to worry, they already automatically match M volume, M surface, M volume, M surface. So what this comment here is doing now, in line 34, I'm going over all the cells. I only have one cell in simulation, so we just grab that single cell, and then I'm plotting for this quantity the x value, which is going to be the time, and the time is called MCS, which stands for Monte Carlo step. Okay, so that's the time unit in our simulations. And the third entry here is the quantity that you'll be plotting on the y-axis. In this case, we are retrieving a property of the cell, which will be the cell volume. So here you can see here in this line here that you have 4 cells in the list of cells. So you are grabbing the cell objects and you're using the dot volume, retrieves the number of pixels that the cell has, and the cell dot surface, the dot surface command, okay, retrieves the surface of the cell, or the number of pixel size that the cell has. Okay, and you are adding the first into the first entry and the second to the second entry. Good question, Sharon. So when this code was inserted, how did you decide to plot volume and surface area? That was just a happy coincidence. Okay, it automatically does this. Okay, because you want to kind of, these are two very basic things that people usually want to plot. But of course, if you want to plot something else, you have to go there and change. Maybe you want to plot the center of mass of the cell. So you change this line here to be center of mass, okay? And then here, instead of plotting, and then center of mass here, and instead of plotting Monte Carlo steps and the cell volume, what you'll be plotting is the x value of the center of mass and the y value of the center of mass, okay? And that's what you do a plot where you actually see the trajectory of the cell in space, okay? Yeah, as Pedro said, the plugins are always added with some kind of example, a predefined value. In this case, the predefined example coincided with what you want to do, okay? But you can also add other things. So if you want to do the ratio of volume to surface, for example, you can just define a new line on line 23, okay? And then on line 38 you can make plot MCS and cell volume / cell surface, and they're going to give you the ratio between those two. So you can, the same plot window can have as many values plotted on it as you wish. What you can also do, you can go back to the line where you define the plot window and copy that and paste again and create a second plot window, okay, where you're going to be plotting different values. Good question, EC or IC. Now, from my memory, I do not remember how you retrieve the cell length. Okay. I think what you would actually retrieve is the cell major axis, minor axis, and median axis. Okay. But there is a way to get it. Okay. Okay. But there are ways to get all these different quantities of the cells. Does it automatically take the mean if you have multiple cells? No, it doesn't. You have to do that manually. If you have multiple cells and want to plot the mean, what you have to do then is add 2 dynamic parameters outside the loop, fill them up inside the loop, and then average them, and then call those 2 functions to populate the plot outside of the cell loop. Okay? All good questions. Okay, you're already thinking ahead. Okay. Okay, so is this make sense? Have anyone try to see if they get a plot in the player? Yes, Ruby got it. Okay. So, uh, so if I run simulation, okay, this, of course, you have to save. Remember to save the simulation, your changes. And when you run simulation, you should see something that looks like this, at least for the very beginning. Okay, sorry. Of course, this keep being populated. So uh, if you don't hit stop at the very beginning, very soon you kind of this will be compressed because the plot is being populated live as the simulation runs. Okay. So did everyone got a plot working on their simulation or not? Yes. Very nice, said Sharon. Okay, okay. So this is a very useful thing to have because when you look at the cell field, you want to see the simulation at that specific time point. Okay, but if you have a graph that's a graph over time, okay, you can actually see the history of the values. Sarana, you have an indentation error. Uh, maybe you can go to the break room and see what was the issue. Okay, you have to make sure. Maybe I can just show my code here. Make sure that those are aligned. Those here at the beginning are also uh, aligned here. Okay, otherwise you get indentation errors. Okay. Yeah, once you start doing the work with Python, you have to be very careful about indentation because that's why I said leave the cursor right there at that specific point. Otherwise, if it's misplaced, then you actually are defining the function outside the instruction outside the function. Okay. The window crashed when I run the simulation. Okay. Uh, the first thing you can try is just to try to run simulation again. If 3D did not close, just try to run it again and see if it works. Okay. So now if you're having problems, I can give some suggestions right here how you may fix it, but you maybe just ask for help in the breakout room where where you can share the screen and see um, how what the typo is or where it is, how can fix it for you. Okay. So did most of you got this the plot work? Yep. Okay. So then let's continue. Okay. And so what you, maybe before you continue, just take a look at the plot. What's happening? You see the volume, which is in red, is going down. Okay. And the surface area of the cell actually goes up a little bit and then goes down. Okay. Do you know what's going up and down?
Hi, Julio.
Yes.
I just posted in the chat. Can you tell me why this won't work?
Cell equals self, selfless. Okay.
Instead of calling cell.volume inside, I've just kind of copied it above and then tried to put it there.
Okay. I'm not sure you can retrieve the cell object by just
Right. It says
asking to retrieve the first entry of the cell list. It should work. Okay. Oh wait. Well, of course, when you
The
paste
cell list is not an iterable. You can't do that.
okay. Okay.
Okay. So James already gave the answers.
Um,
Yes.
why one graph has dots and the other it's a line?
That's is how you specify that here on lines 21 and 22. One is lines of color red of size 5. The other are dots of color cyan. And actually I changed the size in the plots I'm showing to be 4. So if you want both of them to be lines, you can just write lines here on this one. So
All
if
right,
you change
thanks.
that, yeah, okay. Yeah. Basically, that's because you said to be this way. Okay. Again, it comes with lines and dots just to show the different options that you may have. Is there an automated way to make a chymograph? Oh, that would be cool, but I don't think we have it. Okay. There are ways to make histograms, but that will take too much time from this module. I think someone will show you how to do this later. Yes, Rosie will be going over them as the course proceeds. Okay, so if you all have the graph we're working on, I know that you guys are excited to get more things, but let's keep focusing on just exploring the cell shapes. So what I want to do next is, okay, so let's fix that volume problem that you saw before, that cell quickly shrinks. Okay, so you know that we set the initial condition of the cell to start as a 20 by 20 cell, but we kept the target volume to be 50. Okay, so that's why the cell shrinks very rapidly at the beginning. Okay, and notice that because it wants to shrink so quickly, what happens, right, is that as it shrinks, because it's doing in such a hurried way, the surface of the cell becomes rough during the process, and that's why you see an uptake in the cell surface at the beginning and then goes down. So because it shrinks so fast, the cell becomes very rough. Okay, that increases the cell surface area even though the volume is decreasing, and then as the cell keeps shrinking, then the surface goes down again, and eventually the both values stabilize. And in this example, actually stabilize in a very similar value, but that's just a coincidence. Okay, it's just that for this particular value of the cell volume and surface, they are more or less the same. Okay, the cell has 50 pixels, and if you count the sides, that also gives about 50. Okay. Okay, so let's change this the lambda target volume to 400. Okay, and if you do that, save it, and what you should see is that now the volume stays at the same value as was before, and the cell surface, there's a little bit of change, but quickly stay more or less in the same value as it had at the beginning. Okay. Okay, so the cells still are minimized the contact surface. Okay, so that's why it becomes smoother. That's why it rounds up. Okay, but the volume stays the same as before. Okay. You may be a little bit disappointed that the surface area of the cell does not change that much from a square to a surface. Okay, do you know why it didn't change that much?
Sorry, I didn't see where you changed the code.
The code was, I just went to the XML, okay, and on line 28, I changed the target volume from 50 to 400 to match the 20 by 20 initial layout of the cell. Okay. Okay, Sharon answered my question. So the question was, why does the target, why was the cell surface does not change that much? It was a square and now it's a circle. So a circle should have a smaller surface area, but that doesn't seem to be the case here. Okay, and the reason is because of the pixelation. Okay, the way that we count the cell surface is by actually count the sides of the pixels that are in contact with what's not its cell, or in this case the side of the pixels are in contact with the medium, okay? And because you are on a grid, okay, this turned out to be almost exactly the same as the square, okay? So because of pixelation, this value here is almost the same as this value, okay? So because pixelation, you have this. You have to be aware that the cell surface in a pixelized cell is going to be the number of sides and not the line that passes through the it's not the spline line that passes through the pixels of the boundary, okay? Okay, so you have to be aware that cell surface in a grid is just the number of sides, okay? If you have big cells, that doesn't make much a difference, okay? But that's what's going on here. If you now set the target volume to 0 instead of 400, what do you guys think will happen? Please try to do this. Yeah, you can make your volume bigger or smaller, okay? Okay, the question is, what makes a cell circular? What makes a cell circular is the contact energy that you had before. So because the cell wants to minimize its contact energy with the medium, okay, that makes the cell rounder. Because the contact energy is not proportional to the surface of the cell, it's proportional to the number of pixels that each pixel on the boundary interacts with its emitted neighborhood, okay? And because the contact energy is set up in this way, that leads up to the roundup of the cell edges because of the minimization of the contact surface. We're going to go into more detail in a few slides, okay? So if you make the target volume bigger, the cell gonna grow up to the bigger target volume. If you make it smaller, you're gonna shrink to the zero target volume. If you make the target volume zero, what you guess will happen? The cell disappear quickly, set to 0, and that's exactly what happens, okay? So if you change the target volume of the cell either gets bigger or gets smaller. And if you set the target volume to be 0, the cell disappears, which is a way that you can use to actually kill the cells in your simulations. So if you want a cell into simulation that for some reason it should die, you can just set its target value to be 0 and the cell will die, okay? Okay. You can also notice that if you make your target volume to be 10 or 15, the cell also disappears, okay? And I will tell you the reason for that later, okay? So the other thing you can explore is what happens when you change the strength of the constraint. So if you set the target volume to be 1,000, the cell will grow, okay? And keep the target volume to be 2. If you just run that, you should see something that's like this. The cell grows from 400 to 1,000, okay? During the growth process, the volume is a little bit different. The cell becomes a little bit rough, so that's why you see the momentary increase in the surface area of the cell. But eventually the cell reaches its ideal shape. The surface minimization takes place, and then the surface area goes down, and you see now the cell has its new volume, and you see that there are small fluctuations around this value because the strength of the constraint is not that high, it's just 2. If you make that to be 0.5, or 0.1, you see bigger fluctuations from this value in your graph. Does it make sense? Are the target volume and target area independent of one another? They are. Okay, so you set them independently in your XML code. You can make them to be kind of usually if you have a bigger target volume, you want to have a bigger target surface, right? But you can make them to be actually a mismatch between them, and then what you're going to regulate the cell shape going to be the interplay between them and the relative strength of the lambda parameters. Okay, the cell volume and the cell target and the cell surface, the actual volume and surface, they are related to one another, of course, but the target volumes, the target volume and the target surface, they can be very different in your simulation. That would be a way to control the shape of your cells. You can set the target surface to be much bigger than what you expect for a given surface target volume, and that will make the cells to be more rough shape.
Sorry, but if you set a big volume and a low surface area, which one it will choose to strictly follow?
That will depend on the strength of the lambda parameters. Okay. If you make the lambda parameter surface be much stronger, then the cell will shrink to accommodate that volume. If you make the strength of the lambda of the volume constraint to be stronger, then the cell will just grow, and you more or less kind of ignore the surface constraint. But you likely have the cell will grow, but you have very round. Okay. If you make the target surface to be very big and the volume to be small, the cell can actually satisfy both conditions by have a very regular shape. Okay. So James is suggesting you actually try to do this right now and see by yourself how you get those shapes. Okay. So just to actually, I think I'm planning to do this. Yeah, good comment by Sharon. Okay, in real life, if the cell keeps swelling without necessarily add more lipids to its membrane, the cell will burst. Okay. Okay, so if you make the target volume 1000 and let the volume to be 2, you should see this. If you make the target volume of the cell to be 1000, but the lambda volume to increase from 2 to 100, what you should see, okay, I should have asked you guys to do this without showing the result. Okay, so try to do the following. Change the lambda volume from 2 to 100 to make the volume constraint very strong, okay, and leave the target volume to be 1000, okay. So this is what I'm asking to do. Make the target volume to be 1000 pixels and make the lambda volume from 2 to 100, okay. So the shell should also grow, but it will have a kind of different shape than before. So I'm not sure if you guys are we are on the same page here or not. So I'll just proceed and give the answer. So if you make the cell to have a bigger target volume, yes, okay. At least Fatima did it. I'd start a rough circle. So do you get something that looks like this? Yes, okay. So why did this happen? Okay, so like before, the cell wants to grow because you want it to have a target volume that's much bigger than what it had before. But the strength of the volume constraint went from 2 to 100, so we increased it 50-fold. So that's a very strong constraint. Okay, so what happens that the cell quickly grows to its new volume, but you notice that the red and also the blue dots in the graph, once they reach 1,000, they stay there flat. There's not fluctuations, right? We have the random seed. Okay. So what's going on here is that the cell quickly grows to its target volume of 1,000, but because the strength of the constraint is so high, is much bigger, this deep well here of the energy volume respect to the deviation of the target volume is much more steeper. Okay, so any fluctuation from the target volume now will be highly penalized. So it's, once you reach the target volume, because this value here is so high, you actually freeze the cell in this new configuration. So what happens is that the cell quickly grows. Because it's growing very quickly, the shape of the cell becomes very rough during this process, and once it reaches its target volume, it effectively freezes. It doesn't want to accept any more pixel copied after that, and that's why the cell shape stays very rough as before. You are just not allowing the contact energy to round up the cell as you expect from before, because any deviation from the target volume is highly penalized. Yes, Ajay, making the lambda a little bit lower as I had before. So if you reduce that lambda from 100 to back to 2, okay, the cell will still grow, okay, but after it grows, you have time, or will be you are not penalizing the deviation from the target volume that much, so the cell can still fluctuate, so you can still allow the contact surface to minimize the cell volume as you had before. So the slide before here, that was exactly the case. It was the same situation, but a much smaller lambda volume. The cell still grow, right? But after it grows, you actually can minimize its volume. So you have this goes here and stay and relax back. While in the other case, it grows, and once it reaches the target volume, it kind of fixates on that, and the cell is freeze at that shape. The lower the lambda, the more fluctuations you allowed. So you allowed for the other constraints to also have an influence on the cell shape. If the lambda goes negative, the cell disappears. Okay. Because the only way that you can satisfy the constraint is by having a zero volume.
But that's not the target volume, right?
Oh yeah. No, well, okay, yeah, that's not target. The target volume be. So what happens when you make the lambda negative? You are basically inverting your shape, right? And you probably either want to make the cell grow or make the cell shrink. Okay. To maximize the volume, make the cell grow to you probably go against the the contact surface. Okay, so you can also make the cell shrink. That will minimize both the volume constraint and the contact constraint. But once you make the cell shrink, once you get to zero, you have no cell anymore.
Okay. I think I got it to some extent.
Okay.
Although it seems
Try
we
to
are
run another time, Barrett, and see if your cell grows instead of shrinking.
okay, sure.
Yeah, it may grow indefinitely.
Depends
But
if he is starting the volume, the cell volume close above or below the target.
yeah, I'm going to say that exactly right now. Because you right start with the volume that's lower than the target, what the cell will do just shrink. If you make the target volume to be 200, for example, it should grow. Okay, but of course, right now we are doing a nonsensical simulation, a nonsensical set of
That
parameters.
makes a lot of sense actually when I was able to do it with a lower target volume. Yes.
Okay,
Thank you.
good.
Yeah.
It
So,
reminds a little bit, this effect of a negative lambda volume reminds a little bit the foam simulation,
okay.
because some bubbles grow and some bubbles shrink.
Yes, but the growth bubbles that shrink are more from we don't use target volumes for the foam simulation. That's just a minimization of surface um, tension. Okay.
Ah, yes, sure, of course.
Okay. So I do not know what's going on with Sharon pseudo number regeneration, but hopefully the the concepts are clear. Okay, so let's continue. If there are any more questions about this, so here I'm just showing that how those constraints work. So it may be a good idea to make just your constraint much stronger, but if you make it too strong, you get these kind of artifacts where you just freeze the cell, or the cell uh, start to um, satisfy that condition, but after you satisfy this condition, there's no room more for all the other constraints to work on the cell. So that's why you want to allow fluctuations in your cell constraints. Okay. So okay, so this is just a text to explain what's going on. Okay, you can read that later. Um, and of course, the constraint of lambda equals 100 is very strong because not because there's a esoteric meaning with the number 100, is just because that's a very strong number compared to the temperature or the noise level simulation. So if you just redo your simulation with the lambda volume to be at 100 and then you change the temperature to 100, what do you expect to happen? Any guesses in the chat before you do this? So okay, a lambda volume of 100 is freeze the cell because the temperature is 10. If you make the temperature 100, okay, will you get the same result as we had at the beginning, where the cell grows and then rounds up, or not? So try to do this. Yes, lambda affects specific behavior while the temperature affects all the plugins, all the behaviors. Okay. So no, try to do with the target volume of 1,000. Okay, so the cell grows. Okay. Actually, one of our colleagues gave the answer. The result actually not be the same because even though I scale the temperature to match the bigger lambda volume, that also affects the cell adhesion or the cell contact energies. Okay, so you don't quite get the same thing as before. Yes. So look here. So we make the lambda volume 110, the cell grows and rounds up. Now if we make this 1000, it still becomes a little bit rough. The cell is not frozen, it still fluctuates, but the surface is very rough. Okay, it's not being minimized anymore. And the reason that this happens is because relative to the volume now, the contact energies become very weak. Okay, and there's no incentive for the cell to actually minimize its surface. Okay, so the cells are actually fluctuating. You can see here on this graph that it still goes up and down, and maybe it's more clear when you look at the surface value of the cells going up and down. There's a lot of fluctuations. It's not frozen as we had before, but when you actually look at the cell, you see that it's very rough. Okay, and that's because by comparison the contact energy becomes very weak. Okay, okay, so that's basically what I just said in words, so you can watch the you can read by yourselves. So what we can do now is then recover the original behavior by changing the additional energy between the medium and the test cell from to how much. Okay, so you can guess how much you have to change. Okay, you also have to change by 10 to 100. Okay, so if you do that, you should actually recover the same behavior as before. Okay, and then so because a set of values of a contact energy at 100, lambda volume 100, and temperature equals 100, should give the exact same output as the contact energy as a 10, lambda volume as 10, and temperature as 10. If you run those two simulations and compare them side by side, they should be completely indistinguishable. Okay, because all the ratios are the same. Does it make sense? Okay. Okay, so this is just the volume constraint related to contact energy. Let's now explore the effects of the contact energy on our cells. Okay, so let's dig deeper on how the contact energy plugin works in CompuCell3D. Okay, so for the next set of exercises, wait, before I proceed, is there any leftover questions what we have just covered so far? No, all clear? So if it's all clear, let's now explore the effects of the contact energy. Okay, so let's just go back to our 3D and make sure we have all our parameters back to the original values. Let's make the temperature equals to 10, the target volume to be 1000, the lambda volume to be 10, and the addition between medium and the cells to be 10. Okay, so let's reset all those parameters back to the original ones. And once you do that, let's now change the addition between the medium and the cell. So let's make that value to be 50. Okay, can change the number, change the outcome too? Yes, that to be in 6 slides. Okay, we will talk about that. So if anyone have tried this, can you tell me what happened in the simulation? A fully round up cell. Okay. So not only have a fully round up cell, but you may notice that the fluctuations around this shape is also decreased. Okay, because once the cell minimizes its surface area, it's because you have a bigger weight on the energy terms, the cell doesn't fluctuate its shape that much as before. Okay, someone got a square cell. Okay, make sure you have all these parameters to be the same. Temperature 10, target volume 1000, lambda volume 10, and or maybe you set the contact energy to be 500. Okay, lambda surface still should be 0. Okay, if you did not set up to 0, it doesn't have an effect on the cell shape. We want the surface and the length constraint to be 0 for now. So what's happening here is that the cells looks more round and fluctuate less because a bigger energy between the cell and the medium leads to a strong surface minimization of the cell. Okay, so it's better rounded than before, and there are not many fluctuations. Okay. And again, because you make that contact much stronger, once you reach once you minimize the surface, it does not allow for many fluctuations from it anymore. Okay. In this case, it was not that drastic as before. The cell can still change shape a little bit, but there's also always a trade-off. If you make your constraint to be too strong, once it satisfies the constraint, the cell doesn't want to do anything anymore. Okay. Okay, so let's now go to the other side and try to decrease the energy to lower values. Okay. So now if you decrease from back to 10 and even values lower than 10, what happens to the cell shape? What do you expect will happen? Tell me in the chat, and then do the simulation, and then you tell me what actually happened. More fluctuations, yes. That's one of the effects. Because the constraints are a lot weaker. What else happens? Oh, some fragments come off. Well, that depends on how low you set it up. Yes. So what happens now? The cell doesn't have any kind of doesn't necessarily wants to minimize its surface, right? So as long as the total number of pixels is the same, okay, is says target volume. It doesn't care about its shape, so that can lead to the fragmentation of the cell. Okay, so actually, if you make the J between or the contact energy from the medium and the cell to be equals 1, very low, the cell will still have the same number of pixels as before, but it have a very rough shape because not minimizing its contact energy, right? And contact energies have a very low weight, 10 times lower than before. If you actually make the contact energy between medium and the cells to be 0, then actually it doesn't care about its shape anymore. And the graph of this simulation here. If you do this, you should get a very similar graph. The cell very quickly grows to its target volume, okay, of 1,000, but in the process starts fragmenting, okay, because it has no incentive to stay as a coherent structure, okay. As long as it have the correct number of pixels, it's okay, and that will lead to the slow fragmentation of the cell into many pieces. So that's why we always want to have the contact energy plugin there to prevent this from happening. Okay. Your cell becomes square if j equals 1. Was that the j of the medium? Okay. I don't know how that could happen.
Are you sure you were meaning J, not T or something else?
Yeah, if you change the t to 1, it will certainly become a square. Okay. T equals 10. Okay, then I do not know what went on, Victor.
You probably have other energy terms like the surface that are interacting and producing the result, maybe.
Yeah, that's a good point by Pedro. Make sure that your lambda surface is 0 and your lambda length is also 0. Otherwise, they start to take over and change your cell shape. There's a question here.
Yeah.
Okay, there was a question for Ajay. If you have multiple cells, then yeah, everything kind of affects everything a little bit. So it becomes more complicated, of course. So that's why I'm doing all those exercise with just a single cell, so you can build intuition what's happening to a single cell. Then once you get to multiple cells interact together, then you have a better idea what's going on. But then yes, if it starts to become very complicated, change one parameter can affect the other ones. Yeah, also Pedro had give another answer. Okay. So we'll explore multiple cells later. Okay. So let's continue. Let me explain what's going on the contact energy term. Okay. So again, what we are doing that is we are visiting all the pixels that are on the boundary or close to the boundary, and you are summing up those numbers that makes the pairs between the cell that you are looking at, the pixel that you're looking at, with all those other pixels that are within the neighborhood. Okay, So you have a pixel over all the voxels, or of a sum over all the voxels and all the pixels, and then we create the second sum over all the neighboring pixels around that central pixel, and then we do that for this, okay, all of them. That's how we're counting the so in this way of specifying the contact energy term, I and j are, so I is the pixel at this coordinate, j are the pixels around it, okay, at these other coordinates. Sigma here is the ID of the cell, so it specifies either the gray cell or the white cell, okay, and this tau here is going to be the type of cell which this one belongs to, this other one belongs. So in this case, white is going to be is a cell of type medium, and gray, which is the cell ID number 1, will be a type of cell of type test cell, or whatever name you gave to your cell type. So the first sum over all pixel coordinates and then all pixel around it. So you can see that here is whatever value you gave to your that contact energy between gray and white cells, okay, that's being added up 8 times, okay, 1, 2, 3, 4, because that's, you have 8 pairs of this. If you have, but the contact energy between the gray cells and the gray cells, it do not, in this case, well, it is even from the same cell, it does not count. But if you have here another gray cell around it, then you'll be counting those other ones as well, okay. So how do you define how big this neighborhood is? Okay, you can see that if you make a smaller neighborhood, we only take into account the immediate pixels. You can also make a bigger neighborhood, and which is actually gonna take into account a bigger area of pixels to minimize the surface energy. So that's gonna, by change this neighborhood size, you can already have cells that are look a little bit more rough or a little bit more rounded. The bigger the neighborhood, the more rounded your cell is, because it's taking more pixels into account to minimize the surface. Okay, but always there is a trade-offs when you do choose one versus the other. Okay, so this neighborhood is defined with the neighboring order tag in the XML. So if you look at the contact area, okay, plugin, you have the contact between medium, and cell, right? And at the last line there, you have something called neighborhood order, which you usually set up as 4, okay? So the mean of that number is which kind of neighborhood order you're looking at when you actually do this calculation. So a neighborhood order of 1, you're just looking at your immediate pixels, okay? So if this is your central pixel, you're looking at this up, down, left, and right. If you're looking at neighborhood order of 2, then you're also taking into account the pixel neighbors that are in the corners. If you look at 3, then you're looking at a little bit higher, and look at 4, then you're looking at this value, and the bigger you make this thing, the more pixel neighbors you're looking at, okay? So of course, this is how many pixels you're looking around it if you are in 2 dimensions. If you are in 3 dimensions, of course, you're looking at more pixels, okay? Not, for example, neighborhood of 1, you're not only looking at top, down, left, and right. You also look at in front and at the back. So you're looking at 6 pixels instead of 1. And so the number of pixels of voxels scales, okay? It's just by how well, when you set, it's not really the distance, it's more like the next set of pixels that you have the same distance to the center one. Basically, that's it. Okay. So in the simulation, we are using the neighborhood order of 4, which in 2D mean 20 pixels, and in 3D simulations mean 32 pixels around the central pixel. So if I use a neighborhood of the 4, I not only count this one as 4 here at the beginning, I count everything that's within this region. Okay. This neighborhood, and I liked how this plugin contact energy is more related to the cell surface tension than the cell adhesion necessarily. Okay, but yes, it's directly related to the adhesion between one cell and the other. Okay, so if you go, back to your in a hexagonal grid, there's going to be even another way to count. Okay, but I don't have the numbers there in my slides. Yes. Yeah, this higher mean neighboring ought to be a way to smooth out the anisotropy of the grid, exactly as Sharon said. Well, the hexagonal grid, well, you still have an effect. The bigger one, the more round the cell will be. But yes, it's more important in the square grid. Okay, so let's try to explore how this affects our simulation. Let's again go back to 3D and make sure you have temperature equals to 10, target volume to 1000, and lambda volume equals to 10. Okay, and let's change the and keep the adhesion of the cell with the medium to 10. So 10, 1000, 10, 10. Okay, and now with this all set up to this basic values, let's try to change the neighboring order, which set up in line 45 here, from 4 to different value. I either make it higher or make it lower. Okay, and try to check how this affect the shape of the cell. Okay. Okay, I'll give you a few seconds for you to try if you want to do, but I'll just very quickly skip over to the results. I think there's a question. Did someone unmute and ask a question or not?
Julio, I have a question for you from Ajay. He's thinking, obviously he was talking about adhesion, but what is the point of setting a high neighbor order since cells only interact by direct contact?
It rounds up the cell better. Okay. Yeah, the cells only interact if they're actually in contact, right? But the cell have also a small protrusion on their membrane, and then even though they're not touching, if you look at a roll resolution, they may actually be already interacting if they're very close, and that can lead the cells to
Yes, but you notice you are justifying you're justifying the use of a computational artifact because of the effect, and you're not justifying because of biological processes, you know. So this is a little bit tough to answer. I don't know, what do you think about it?
Okay, you have to remember that the cells are always fluctuating its membrane, so even though they're not touching, they eventually touch. You can also, if you look at the cell surface closer, the cell has lots of protrusions, small protrusions, small filipodia, or some villi outside the surface, so they actually may be interacted at a close range. Of course, you never make the neighboring order to be the same as big as the cell radius, because that will lead to the disappearance of the cell. Okay, but uh, the neighbor order will always go a little bit over the cell surface. Okay. Okay. So yeah, it always depends. Okay, how big is your target volume of the cell? Okay, and compared to how big the other cell is. So all these things will depend on exactly on your situation. Doesn't make some biological sense. If not, you can just reduce your neighbor order from 4 to 1. Okay, and that will, if makes more sense for your simulation. So let me just try to round up. So if you change the neighboring order to a lower value, what happens is that the cells still are minimizing the contact energy, okay, locally, but going to be very locally. So we have lots of very localized surface minimization, which makes the cell very rough, like this. It's kind of straight lines, is minimizing the surface, but it looks squarish, okay. A neighboring order of 4 makes a little bit smoother, okay, and a higher neighboring order actually makes the cell, because it's looking over a bigger area to minimize, is actually make the cell much smoother than a neighboring order of 4, okay. So this is look a little bit what happens when you change the contact energy, okay. And but there are and the idea because why this looks like this, why this looks like this, is because when you change the neighboring order, you are changing the number of things you're summing, okay. So if you use a higher neighbor order, you're summing up more elements, so that's equivalent to also increasing the contact energy of the cell. When you're using a smaller neighbor order, you're just summing up small fewer pairs, so that's the equivalent of using out. It's not equivalent, but very similar to using a smaller contact energy. Okay. So I see that are a lot of good question and points being up in the chat, and we are very happy with that. But I'm already very over my allotted time. So these slides are made up on our Google Drive. Okay, so there are more exercises that I suggesting here to do. Here I try to compensate the neighboring order with the J's to see if you actually get the same result or not. You don't actually quite get it. Okay, you have start having pinning effects in your simulations. Then here are some slides that explain how you count the surface. Here in the next set of slides, my plan was to go over what will be the effects of the surface constraint of the cells and how you count surface in a grid. Okay. And there are a set of exercises for you to explore the effects of surface energy. And I think one of the exercises actually have a mismatch between volume and surface to see which one's going to win. Okay. And then if there's a big mismatch, you can leave the fragmentation of the cell. Okay. Then the last set of exercises that I had planned for today was look at the effects of the length constraint, what happens when you force the cell to have a given length. Okay. And there's an interplay between that and the surface of the cell, of course. So here's what happens if you increase that length constraint from 40 to 60 to 80, okay, to make the cells elongated, okay. And unfortunately my time is over, but you can always go back to the Google Drive and try to do those things as for yourself as homeworks, okay. And I will stop here, okay, and I'll ask you, thank you for your attention and your patience. And I see there's a lot of discussion going on in the chat. I don't know if James wants to take over and ask something. What I'm
So
doing
Julio,
now.
two things. One, you
Yes.
should run your module questionnaire.
Yes.
And two, If you need it, would people prefer that you take another module and finish your lecture and push Gilberto's lecture to tomorrow? How much time do you need?
I'll need more. I guess with the space if it's going it's more 45 minutes, maybe just good for Gilberto to do, and then I maybe can do over lunch tomorrow. Or maybe people can do that as homeworks. Okay.
Yeah, I think maybe we should move to Gilberto's module if you don't feel like you have a
think
full
so.
90 minutes worth.
Okay. So please do the questionnaire. Is this one that's open already, your questionnaire, or is it a different one?
That's an old one, I think.
Okay, so please fill out the questionnaire for Julio's class.
Pradeep and Sharon were talking about a case where your cell occupies all the lattice and there's no medium, your cell don't shrink. This can happen in a situation, for example, when you have a tissue with no space between the cells. You don't have medium around the cells for them to separate. You always need to separate the cells from the outside. So one way of dividing the cells even in a conformal tissue is to build a simulation in 3 dimensions to have medium above the cells. So pixel mediums, medium pixels can penetrate between the cells in the tissue, and then you can separate the cells from the middle of the tissue instead of only starting in the border. So this is a very this problem of not having medium available to separate cells, for example, or to shrink cells, can happen when you don't want. So a 3-dimensional simulation probably is the way to go.
I'll say that 3-dimensional simulation is also a way to model the cell adhesion to the substrate, but not necessarily the medium around it. So that was a question in the first module that asked, okay, how can I model the cell adhesion to the substrate and not to the other cells or the medium around? If you have a 3D simulation, that's a way to do it, because then you can define something below that has a different cell type, and then the cell will walk on it. Okay, and there have many simulations and papers that look at the movement of the cell and change the adhesion of the cell with the substrate below. Okay, there's another way. There's a work by, there's this publication that looks at how the surface topography and the surface adhesion affects the migration of the cells. It was done by a French group. I forgot the name of the. I think it's Rachel. Forgot her surname, but that'd be also a way to do this. So this is going back to the question we had on the module before.
Over the surface of some other cells, like we just talked about a little earlier, you get a little bit of a paradoxical effect. So if the cell A, let's say, is moving in response to some movement potential, but it's moving over cell B to which it has adhesion, then if you increase the adhesion of cell A to cell B, instead of the cell getting stuck, it moves faster, because the penalty for moving to a new spot is lowered rather than increased, I guess, because it remains in contact with the same cell type. So what is a better way to implement the cell getting sticky and adhering more to the substrate? Because increasing the adhesion, actually, it has the opposite effect. The cell is allowed to move faster.
So are you having a situation where you have a, so it's a 3D simulation?
No, it's just a 2D simulation, but there's a column of cells that's
Okay.
moving over the surface of some other cells, which is stationary. And
Okay.
the column of cells is moving under some potential force along the x-axis. And
Right.
we were trying to simulate what happens when the adhesion between the moving column and the substrate becomes higher. And intuitively, you would expect that to slow the migration. But in the simulations, it actually lands up moving faster. And I'm guessing that's because if you lower the energy, if you move the pixel from one set of cells of one type to the same set of cells in another position, there's not much of a penalty. The penalty is actually lowered. So
Yes, you're right.
So it turns out that's not the better way to implement increased stickiness. So I'm trying to figure out whether there is some advice about, in this kind of cellular context, what's a better way to implement your substrate becoming stickier?
Well, if you decrease the energy between the cell and the other cell which move on, that should lead the cell to spread more over it. Okay.
Yeah.
But yes, when the cell moves around it, okay,
Yeah.
by the fact that it's moving, and if it keeps the same surface with the cell, that has no effect on the adhesion energy, right?
Right.
So like this, and the cell can slide over the cells and still keep that same energy, the same. So you're not necessarily, you're increase the thickness in the sense that it's like to spread over, right?
Yeah.
But you're
So
not
would it be
increasing
better
thickness in
to?
the sense that it can still slide and there's no penalty on the energy.
So should I increase the lambda?
No, actually, what's going on when the cell becomes, yeah, that's, so the way that you solve that, okay, what's going on when the cell stick to the thing below is that well, one of the things that you can interpret is that the cell is creating adhesion points,
Yeah.
okay, focal points of adhesion between the cell membrane and the substrate, okay.
Yeah.
And that may something that it might be something that you want to model explicitly by adding a link between the cell and the
Right.
surface, or you can create a little compartment inside the cell that actually attaches to the substrate, and it does not move.
Right.
And there are other ways to go about this. Gilberto, the teacher for the next module, is someone
Yeah.
that's actually is modeling adhesion points in CompuCell.
Okay. Okay. Maybe I'll get some ideas from there too.
Yeah, but yeah, the adhesion. I mean, you can still slide to cells, a cell over a surface, and that makes no difference with adhesion. Okay.
Yeah. Because
In terms of the contact energy, it makes no difference. right?
Yeah, because it
And
still has the same surface available when it moves. And in fact, when you lower the energy, it is happier to move because it still satisfies that condition. It's kind of a paradoxical thing. We had our cells moving between two layers, an overlying layer and an underlying layer. And we were trying to see in a particular context adhesion to which layer was more important. And but we had this sort of paradoxical outcome. So we sort of didn't use the model for that exploration any longer.
I can add to it. So the idea Gilberto is using to build his model on adhesion points is to, for example, we have the interface between the cell and the substrate the cell is walking over on.
Yeah.
And you create points, pixels.
Yeah.
In this interface, and the pixel has a very, very high lambda volume, so it doesn't disappear.
Got it.
But it has a decay time.
Yeah.
So when the cell tries to walk, the point will pin the cell in place.
Perfect.
So this is the idea that Gilberto is using to develop this adhesion idea, this adhesion model, but
Correct.
it is very much more complex than any plugin that we have
Yeah,
in the basic.
Hi. Yes.
What are you doing?
I'm just entering the conversation.
But you need to be taking off.
So Gilberto can talk a bit more about it. And we also, I'm thinking about suggesting Gilberto to do a lecture specifically about this topic in Friday, that we have
Cool.
some slots there. So you're not the only one asking for this type of process, biological process of adhesion. So we can think in some specific content about it.
Thanks very much.
Okay, this is great conversation, but this is exactly why we have the morning and the afternoon times reserved for discussion. So we have to try to stay on cue a little bit for today because we have so many people from different time zones. So let's move on to Gilberto's presentation.
The Slack group is also a place to continue these conversations offline. Well, online, but off meeting.